what's coming up. Worst topic in the entire book is this. 2.7, inverse functions. There is only one direction for inverse functions. And you'll hear me say it over and over again, and then when you get confused, you'll hear me say it over and over again. There's not much to it. So if I tell you that f is a set of points, say -2, 5, -1, 7, 0, 4, 1, 2, and 2, 0. That sounds good. Number 1, is f a function? Gotta make sure of that first. Of course, I told you it was a function, so it better be. But can you tell it's a function? Why is it a function? There's no repeating x's, and for every x, there's only one y. Okay. Another way of looking at this is f is going to do something to the domain. Let's say -2. And it's going to bring -2 to +5. Because -2 is associated with +5. So one way of looking at this is f is going to operate on this -2, do some kind of calculation to it, and bring you to +5. Easy enough, I could make like f of x is equal to x plus 7. And if I plug in -2, -2 will generate +5. But that's not the way I want you to look at this. But that's a way of looking at it. So, -2 is going to 5, -1 is going to 7, 0 is going to 4, 1 is going to 2, and 2 is going to 0. What do inverses do? Like, for instance, if I have 2x minus 3 is equal to 7, how do inverses apply to this equation? Solve for x. What would you do first? You would not subtract 3. Oh, did you? I thought you said subtract. You would add 3 to both sides. Now stop here. What are these two called? Inverses. They undo what was done. Instead of taking 2 times a number and taking away 3, this will do the opposite of taking away 3, which is adding 3. So then you get down to 2x equals 10. I'm taking word division from you, so how do I solve for x? I said I'm taking the word division away from you, so how do you solve for x? No, I said you can't use that word. Multiply by 1/2. So if you multiply both sides by 1/2, what are these two called?
They are called fractions.
Now, they're called an inverse, multiplicative inverse. And they turn out to be 1, and you get x equals 5. Inverses allow you to solve equations. They allow you to solve equations because they undo what was done. Well, the same thing applies to functions. You can undo what a functions do. For instance, f takes -2 to 5. To undo it, all I have to do is take 5 and bring them back to -2. What that does is just takes the domain and range and switches them. That's it. All right, so we're going to label this that. This is not f raised to the -1 power. This is not f raised. This is not 1 over f. This is read f's inverse, or the inverse. Inverse of f. F inverse, or the inverse of f. Now, if we do f inverse here, let me do it in a different color. We would say, well, we want to go backwards. So if -2 goes to 5, f inverse is going to take 5 and bring it to -2. And if -1 goes to 7, this becomes, so you get 7, -1, and 4, 0, and 2, 1, and 0, 2. Great. This would undo everything that was f does. So as f takes -2 to 5, f inverse takes 5 and brings you back to where you started, which was -2. Now, are all functions invertible? This is called an invertible function. Oh, by the way, is f inverse a function? I better have it calling a function because I'm saying it is a function by its notation. So is it a function? Yeah, 5 goes to -2. 5, 7, 4, 2, and 0. The domains do not repeat. Perfectly fine. So I guess that begs to differ. What if I have a g function that looks like this? Real short one. -2, 3, 0, -4, 2, 3. First off, is g a function? Yes. Now, if we invert it, it more than likely won't be because I've made it up this way. So g inverse question mark. If I invert it, I get 3, -2, -4 is 0, and 3, 2. What's wrong with that? I got repeating x's all of a sudden. I have a 3 there and a 3 there, and they're going to different ranges. So this is not a function. So what we're going to say is g is not invertible over its entire domain. I'm not going to say that g is not invertible, period, end of conversation. I'm just saying it's not invertible over the entire domain. To make it invertible, I either get rid of the first point or I get rid of the last point. I can do that. I can throw things away and constrict my domain a little bit. We'll talk about that later. So what's the difference between f over there and g over here, other than f is invertible and g is not? How would you describe their difference? How do I know this one's not going to be invertible before I even invert it? No. There's repeating y's. Over here for functions, you're worried about repeated x's. To make it invertible, you have to worry about the other variable, which is repeating y's. So if we want a definition for this, we're going to call it one-to-one. A one-to-one function has no repeating x's and no repeating y's. The wording of it is a little different. A one-to-one function, for every domain, there exists. This sounds very much like the definition of a function. For every domain, there exists a one range, right? That's the definition of function. It gets a little funny wording here now. For every domain, there exists a unique range. What's unique mean? One and only. One and only. So if we were going to look at, the graph of functions, kind of like, when I was doing graphs, is it a function or is it not a function? Can you tell which one of these is a one-to-one function and which one is not one-to-one? Just by looking at it. You should be able to. So how would you determine if they were functions? Bless you. The vertical line test. You'd pass a vertical line through it, and if it only hit the graph once, you'd say, oh, it's a function. Well, they're both functions. So how do I determine which one's one-to-one and which one's not? No. Think about this. It's a function if it's this way.
Oh, the y way. Meaning
This way.
horizontal line.
Horizontal line. If I pass a horizontal line through, what it's saying is, for this one x value down here, there is exactly one y value, and it doesn't repeat because there are no intercepts other than that one. But if I draw this horizontal line, it's saying, well, this x has this y, this x has this y, and this x over here has this y, and all those y's are exactly the same. So this one is not one-to-one by the horizontal line test. So it's similar to the vertical line test. It's vertical line for function, horizontal line for one-to-one. And this one is one-to-one. That's an abbreviation for one-to-one. Ratio notation. So the first one does not have an inverse for its entire domain. Maybe I can cut it up into a smaller piece and have an inverse, but it doesn't work for just the entire domain. This one does. So what's another way of recognizing a graph that is one-to-one other than the horizontal line test? Well, if you look at this graph, what's it doing from here? I'm going to do it in green. What's it doing from here to here? It's increasing. What's it doing from here to here? Decreasing. Once it does an increase and a decrease, it's automatically not one-to-one, because that means you're going to have a horizontal line pass through something. Because one's going up and the other one is coming down. So you're going to repeat it. What's true about the second graph?
It's decreasing.
Always. It's never ever turning around and going, oh, I'm going to increase for a little while and then turn around and go back down. It's always going down. So a one-to-one function is either always increasing or always decreasing, and it has only two options. All right. So what can I do with an inverse function? Well, find the inverse of a function. There's not many steps involved, but one of them gets a little tricky. To find the inverse of a function, to find the inverse of a function, number one, change your function notation back into old notation. So in other words, change f of x, g of x, h of x, whatever it is, back into regular old y. It just makes the work afterwards a little bit easier. Number two, change what you have there, x's, into y's, and y's into x's. Actually, it's just y. There's only one y that's going to be there. Okay. Now, at this point, right here, step one is still talking about the original function. Step two is really talking about the inverse function. We're not talking about f of x anymore. We're talking about its inverse. Step three is the hardest. Solve for this new y. It's not the original y, it's a new y. And then 4 is the step that everybody forgets. Change y back into function notation, but the function you ended up with is now called f's inverse, or the inverse of f. The inverse of f. All right. So the steps really aren't that hard. It always comes back to take your domain and range and flip them. And step two is exactly doing that. It's taking your x's and y's and reversing them. So whenever you're lost in inverse land, just go back to the idea that the domain and range are flipping. For example, I forgot one little piece. Prove f of x is equal to 3 x cubed minus 7 is 1-to-1, and then find its inverse. How the heck am I going to prove that it's 1-to-1? Well, it kind of comes back to the picture of the one-to-one function. For every x, there is exactly one y, and it happens to be unique. So what you do is you make an assumption that you have two different y values, and you show the x values have to be, or these two different, you show that you have these two y values that are exactly the same for two different x values. If it's 1-to-1, the x values must be exactly the same. So let me write that down. Definition of a 1-to-1 can also be written this way. If you're given a 1-to-1 function, and it's called f of x, you assume that you have this f of a is equal to f of b. If this is a 1-to-1 function, what you're saying here is you have two different y values. You have the exact same y value for two different x values. But what has to be true about the x values if it's a 1-to-1 function? They have to be equal. So a has to equal b. Then A equals B if f of x is 1 to 1. Well, it's kind of another definition of 1 to 1. If you have this set up and A equals B, then f of x is definitely 1 to 1. You can solve a lot of equations with this too. We'll get back to our example up there in a second. For instance, if you have 2 to the x is equal to 8, you'll see these in chapter 4. A little preview. Can you solve for x? How do you know x is equal to 3? Yeah, so I can rewrite 8 and write this as 2 to the x is equal to 2 to the third. By the 1 to 1 property, this function 2 to the x, by the way, is 1 to 1. You can look at this and go, well, the y values are equal, therefore the x values have to be equal. So you can write x is equal to 3. What's cool about this is a non-algebraic step. It has nothing to do with algebra. You didn't add something to both sides, you didn't divide by something, you didn't multiply. You just got your answer by a property of 1 to 1 functions. You're just saying, oh, the y values are equal, therefore the x values must also be equal. It's kind of a cool step. Alright. So let's go back to our little function up there and prove that it is 1 to 1. So the first thing you do is you write, well, if I'm going to prove that it's 1 to 1, then we make the assumption that I have this f of a is equal to f of b. Trick question of the day. In my other class, sat there for 2 minutes answering this question. What's f of a equal to?
A.
No. What's f of a by itself equal to?
0.
What's f of 2 equal to? How would you find f of 2?
Oh, you put the 2 on the A.
Oh, you put the 2 into the x. What's f of a equal to?
You put the A into the A.
You put the a into the x and you get?
3.
You put the a into the x and you get?
3 times A to the
3a cubed minus 7 is equal to, what's f of b?
3B.
3b cubed minus 7. Do you see how silly that is? Y'all know what to do, you just don't want to actually go through the steps to do it. Now, when you get to this part here, there's an invisible rule. It's basically solve for a. It doesn't matter which one you solve for, but usually people choose a. So when you start solving for a, what happens to the 7s? They both cancel and you get 3a cubed is equal to 3b cubed. What happens to the 3s? They cancel and you get a cubed is equal to b cubed. How do you get rid of a cube?
Cube root.
You can say it a few different ways and I'll eventually do it.
Wow.
If you cube root both sides, you get a is equal to?
Wait.
That's a good question. Is it plus or minus b? Or is it just b?
Plus or minus B. No, that's only with
It's only with an even.
even, yeah.
It's a equals b. So since a equals b and doesn't equal anything else, we know that this function f is 1 to 1. F is 1 to 1. Great. Now let's find its inverse. Because you can only find an inverse over the entire domain of a 1 to 1 function. So to find the inverse of f of x is equal to 3x cubed minus 7, the first step is, number 1, change f of x into y. So you're going to get y is equal to 3x cubed minus 7. I haven't changed anything, I just changed notation. The next step, you take the domain and range and flip it. So the y becomes x, and the x becomes y. Now we're talking about something different. Those are two different things. One is the original function. The one underneath the little squiggly line is our new inverse function. And then the hard part, we got to solve for y. So what do I do first? Add 7, so you get x plus 7 is equal to 3y cubed. Divide by 3, you get x plus 7, all divided by 3 is equal to y cubed. Cube rooted, you at least got the language down. And you get y is equal to the cube root over the entire thing, x plus 7, all divided by 3. Now, a lot of people stop here, but you have to be careful. What you're saying is then this y is equal to the cube root thing, and this y up here is equal to the cube thing. But they're different, obviously. So what you have to say finally is this is not really y, it's really,
F of X.
nope,
X.
no, f's inverse. Because what we're looking for here was an inverse. So you have to replace this last y with the inverse notation of f.
You're gonna take off when you get there.
Gosh, yeah. Because if you leave it as y, I don't know which y you're talking about. This one? That one?
All right.
You gotta be really explicit. Alright, now here's the cool part. What is, let's pick a nice one. That doesn't really matter. If I come over here and I say, let me put a little box here. What is f of 1? What is f of 1 equal to? F of 1. What do I do with the 1? Plug it into f. Don't look at f inverse down here. It goes into f. So it would be 1 cubed, which is 1, times 3 is 3. 3 minus 7 is? Negative 4. All right. What is f's inverse of negative 4 equal to? Okay. Now I have to look at this one down here. That's one. So you plug in negative 4. Negative 4 plus 7. 3. 3 divided by 3. Cube root of 1 is? What happened? Well, f took 1 and brought you, f took 1 and brought you to negative 4. F inverse took negative 4 and brought you back to 1. It's kind of cool. One goes someplace, the other one brings you right back. So trick question of the day. You write it in green so it comes out really sharp. What is f of f's inverse of x composed with each other equal to? One takes you someplace, the other one brings you back. Ready? Where did I start up here with this? Where did I start? I started with 1. What did I end with? 1. What am I starting with here? What am I going to end with? X. It brings you back to where you started. So you get these two things, which are extremely important for functions. This one is also equal to x. Little box, big star, couple of them. This is super important. This is the purpose of inverse functions. Why? Because if you look at it, what happens with the f and the f inverse? They kind of go poof, and you're left with what's inside. They're not canceling. Don't say cancel, because cancel is inverse identity. There's no inverse identity going on here. The functions run into each other. They kind of go poof, and they leave you with what is inside. So maybe a little bit more explicit with that.
You say poof.
Poof. You can't say cancel, because our shortcut cancel is an inverse and then an identity. And that has nothing to do with that stuff there. So what if I write something like this? F inverse of f of x squared minus 2. What do you think it's equal to? X squared minus 2. Because the f and the f inverse kind of go poof. They kind of go poof and they magically disappear under the inverse property. If I write f of f inverse of g of x. Nope. G of x. The f and the f inverse kind of go poof, and you're left with what's left over. It's a neat property. Very powerful. Alright. Much time. Plenty of time.
But why do we have to go? What's the difference of those and that one right there? Because you have all that work and then you
Oh, this one is our original function. This is the one that will undo it. I need to know what will undo an original function so that I can have it go poof. If I do compose them with one another. Individually they work pretty cool, but together they work wonders. It's kind of neat. Let's do one more find an inverse. Example. Yeah. The hardest one is this. It's a rational function. It is 1-to-1. It is 1-to-1. I'll just give that to you. We're not going to do f of a equals f of b. It takes way too long for this one. So it is 1-to-1. G is 1-to-1. So I can just go and find its inverse. So the first step of finding an inverse, yes, I'm asking you to turn back a few pages and say, change g of x into y. So you go y equals 2x minus 3 over 4 plus 5x. Okay, and then interchange your x's and your y's. So this becomes x is equal to 2y minus 3 over 4 plus 5y. Make sure you change both of the x's into y's. All right, now the hard part. I need to solve that for y. What would be the first step? Multiply both sides by 4 plus 5y. The common denominator. Get rid of the fraction. Just like any old linear equation. Get rid of fractions, get rid of parentheses, all that fun stuff. That'll bring me to, I'm getting too tall. Let's see, on that side you're going to get 4 plus 5y times that x is equal to, what's left on the other side?
2y minus 3.
2y minus 3, because these are just going to cancel out. Cancel, not poof. That one actually cancels inverse identity. And you're left with 2y minus 3. Multiplicative inverses. All right, what's the next step of solving a linear equation? Got to distribute the x, so we're going to get 4x plus 5xy, alphabetical order, but if you write it as yx, I'm not going to worry, is equal to 2y minus 3. Okay, now what? We're solving for y. Yeah, you always want to get that in your back of your head. Do what? Nope, I wouldn't touch the 3.
Subtract the 4x.
Nope, wouldn't touch that either. What are you supposed to be concentrating on? The y. Why do you keep moving terms that have no y's in it? I have a y here, and I have a y here. Where do they need to be? Same side. That's your goal. Get the variable you're solving for in this. Remember, you have to go back to chapter 1, section 1. Read that long list of how to solve a linear equation. So which one do you want to move? Subtract 2y. So this becomes 4x plus 5xy minus 2y is equal to negative 3. Then what? Move that 4x because it has no y's in it. So we're going to get 5xy minus 2y is equal to negative 4x minus 3. Say it again. Factor. What can I factor? The y is the only thing I care about. So I'm going to kick out the y. What's left behind is 5x minus 2 is equal to negative 4x minus 3. Divide by 5x minus 2. So you get y equals negative 4x minus 3 over 5x minus 2. Woohoo! Of course, there's one more step, and you can't stop here. You need to replace this y with what it's really equal to. It is not equal to g of x. G of x is that thing over there. G inverse of x. So this becomes g's inverse of x is equal to, now, if you look in the back of the book, you won't find that. You will find this, though. Are they the same? Yeah, they're the same. All I did was multiply top and bottom by negative 1. That makes the entire top positive, and it takes the bottom and actually flips it. Becomes a positive 2, so I might as well put that first. It makes it a negative 5x, so I might as well put that second, because I like minus signs in the middle. So this would be your final answer. That is g inverse of x.
So we are.
And the g inverse of changing it from y to x is to the g, or to the inverse is, that's step 4 of the
Step 4 is replace it with its inverse notation.
Alright, on that G, on the inverse part, the G inverse, if we were to press on that for you on the test, if we left it the other way.
Oh, if you left it the blue way, that's fine.
Alright,
It's just the book will have it this way. So you'll just have to go, oh, all the signs changed. It's the same answer. But yeah, if you leave it the other way, that's fine. Oh, plenty of time. I got one more little baby topic to cover. And it's not a very hard one. Graphing and inverse. To graph an inverse function is actually a very simple thing to do. For instance, if I give you original function, let's say, here's my graph. Notice this graph is always increasing, always going uphill, so it is a one-to-one function. This won't work really well if you invert a non-one-to-one function. So basically, I'll give you a graph that looks, well, it actually can look like anything, but this is a nice simplistic way of looking at it. If I don't give you what these coordinates are, if you can't figure them out, make them up. So what does this point look like? The first one here to the left.
we'll just say
4, 2 is over here.
negative 4.
Negative 4, negative 2. Negative 4, negative 2. Oh, about this one here. 2, negative 1. It has to be higher than this one, otherwise you won't be always increasing, so be careful. This point up here, 3, 4. Sounds reasonable. This one here I'm going to be really explicit with. Let's say that is either 6, 6 or 5, 5. But the x and the y, I try to make them exactly the same for that point. I know this because I kind of did a little line through it, y equals x. All right, to find the inverse function, all you need to do is take your domain and range and function. So literally hit each one of those points, flip them, plot it, see what happens. So negative 4, negative 2 is now going to be plotted at negative 2, negative 4, someplace down here. So here's negative 2, negative 4. Oh, I forgot to label the blue graph. Let's let the blue graph be f of x. F of x. And the black one here will be f's inverse. What about 2, negative 1? Negative 1, 2. That would be right about here. Negative 1, 2. 3, 4 would become 4, 3, which would be right about here. Actually, I'm a little bit off there. And then 5, 5 becomes 5, 5. It would land right on itself. So the new function would look something like this. I actually messed up that 4, 3. Now, after you graph this, take your paper, rotate it 45 degrees to the counterclockwise direction. There should be a line that goes right down the middle of it that it reflects over. You all know what a reflection is, right? Let's test it. Ready? If I have a line that's like this, and I have this shape on top of it, what would its reflection look like? No. This would look like that. This little line segment would look like that, and then you'd have this bubble here. So what I'm looking for is this this blue line is reflecting over that dotted line to give you the black one. So it's a complete symmetry going on there with this dotted line. The equation of this line is y equals x. It's a line of slope 1, up 1 over 1, up 1 over 1, that goes right through the origin. Okay. So one last type. That was an always increasing one. Let's see what a decreasing one would look like. Let's say this is g of x. I want to graph its inverse. Well, notice I didn't give you any points on this one. So what would you do? Make up some. I'm going to pick this point, and this point. So the far left one, give me a reasonable coordinate for that. -4, Negative 4, 4, that'd be fine. This point here, 0, 1, that's a good one. This point way over here, it can't be 6, 0 because it's not on the x-axis. And it can't be 6, 1 because it always has to be decreasing. That one.
0.5.
6.5. That sounds good. All right. So if I take all those points and switch them around, what do I get? Well, negative 4, 4 becomes 4, negative 4. That's way over here. 4, negative 4. 0, 1 becomes 1, 0. That's right about here. And 6.5 becomes 0.56 up here someplace. And you get a graph that looks like this. You have that idea that there's this line that goes right down the middle. The graph has to reflect over this line. So this branch has to reflect over into the first quadrant. This part here has to reflect up there. It's going along the x-axis, so over here it's going along the y-axis. So this graph would be g inverse of x. So graphing them should cause no problem because all you have to do is take the domain and range and reflect it. Just be careful of the curve. All right.